Hey everyone, Adam the Tutor here, coming at you with part D of our harmonic oscillator series right here. So basically what we're going to do in this part is we're actually going to have to end up solving the differential equation again, right? Because this time what we've got going on is we no longer have, the situation where, like maybe we hold the mass at a certain position and let it go with a certain velocity and then just leave it to its own devices. Now we've got this driving force that's attached to it, right? So basically what that means is that now we're going to have the situation where we have x double dot plus gamma x dot and then plus omega naught squared is equal to some forcing function f of t, right? Actually, maybe I shouldn't call it f of t because, as you'll see here in a little bit, I'll call it g of t, right? That way, just to be consistent with my notation that I have below. So basically, and our g of t's, of course, are right here in part D. So for case 1, g of t is equal to c times the Dirac delta function of t minus t sub d. And number 2 is g of t, which is equal to c times the unit step function t of t sub d, and then cosine omega t minus t sub d. And then number 3 is g of t c times mu of t minus t sub d. So if you'll notice, basically 3 is the same as case number 2, but with omega equal to 0, right? So, okay, so we have 3 different g of t's, right? So we could go through the process of solving each of these. We could go through the process for solving for each of these functions, right? Because we'd have 3 different differential equations we basically have to solve. This one, and this one. And I don't know about you, but that's a really long process. We could do it. We could totally do it. But that is a lot of work. And my motto has always been, the more work that you have to do, the greater chance that you're going to make a mistake. So, in lieu of solving 3 separate ones, what we're going to do is we're going to use a method called the Green's function. Green's function. I think I'm spelling that right. There's a E. Yeah, Green's function. Right? So this is the method that we're going to use. And you might be asking, well, okay, what's a Green's function? And how do we even use it with this problem? Oh, and there should be an X here. Right? Okay, so this guy right here, and I'll write in this part in a blue color, in a nice light blue color. This is a Green's function. And more specifically, this is the Green's function for our operator up here, right? So this is the Green's function for, we have a second order time derivative, and then plus gamma times a first order time derivative, and then plus omega naught squared. So this is the Green's function associated with this operator. And if you'll notice, this is the operator that's operating on the function x, right? And I'll do a separate video where I go into a greater length as to how I got this and, what's the theory behind it and all that good stuff. But for now, just know that this is the Green's function that we're going to be working with. And how it applies to our situation is, well, we can solve for this f of t here is really our particular solution, right? This is our particular solution, right? For a g of t prime, right? So, with that in mind, well, basically all we have to do is just evaluate three integrals. And evaluating three integrals is less of an intensive process than trying to solve three differential equations, right? Okay. At least, if the integral is nice. Which, one of them might be kind of long, but, you'll see that it's not really too bad. Okay, so that was kind of a long, kind of basic outline. But let's actually go ahead and do one, right? Okay, so the first one is when we have g of t equal to this Dirac delta function, right? So now I'm going to switch back to black here, okay? So this is case 1, right? So then our particular solution here would be integral from 0 to t mu of t minus t prime exponential e to the minus gamma over 2 t minus t prime, and then we'd have sine of gamma t minus t prime, and then over gamma, and then our g of t prime is going to be c times the Dirac delta function of t prime minus t sub d, right? And then dt prime. And I'm going to go ahead and, well, no, you know what? I won't assume familiarity with the Dirac delta function. Okay, so this Dirac delta function, its entire purpose in life is to be in an integral. Like, that is the sole reason that this function exists, and it's what's known as an area-defined function. And just for some quick properties of the Dirac delta function, so let's go over here. So these are just some properties of the Dirac delta function, right? You could, let's just do t minus t prime d dt, or what? Yeah, sure, why not? This is equal to 1, provided that that t prime, well, I mean, of course, t prime is, as long as it's finite, then we can guarantee that it's in this interval. But, this could be a finite interval. This could be the integral from a to b of the Dirac delta function of t minus t prime. And as long as we'd have t prime in between a and b, this would still be true. So that's one property. Another property is that we have the following is equal to 0 for t not equal to t prime, and it diverges off to infinity. For t not equal to t prime, and then for t equal to t prime, right? So basically, we're going to use these two properties of this guy right here to simplify our integral. Well, how are we going to do that? Well, remember what I just said, right? It's 0 if t is not equal to t prime, right? So then basically, in order for the particular solution for x not to be 0, we have to have that t prime here is equal to t sub d, right? So basically, all these t primes become equal to t sub d over here, So then what we have, and let me go ahead and switch back to black here, is we have that x sub p of t is equal to the integral, actually. So I want to go ahead and factor this out, right? Because now all of these terms, this mu, the exponential, the sine, they are not dependent upon t prime anymore, right? So we're going to have mu of t minus t sub d exponential gamma over 2 t minus t sub d sine, and we're also going to have a c over here, and let's just do c right there, sine of gamma t minus t sub d over gamma, and I need a parenthesis right there, and then times the integral from 0 to t of delta t prime minus t sub d dt prime. Well, remember what I said, now we're going to use this first property over here, right? This first property over here, right? Because now we have an integral, and so basically the question is, well, you know, is TD less than t and greater than 0? And the short answer is yes. So basically, this whole guy right here just goes off to 1, right? So then we're left with, and I'll underline this, I will square this, or box this rather, in blue. So what we got here is the following, and that's getting kind of wavy. Whoop, didn't mean to do any of that. There we go. Okay. And so this is our answer to case number 1, right? And, you know, I had to do a little bit of explaining, but it wasn't too bad, right? Okay, and I think I'm going to leave this video here because I'm going to need a little bit more time with the next integral, but we can probably do the next 2 integrals in one video, and, you know, it'll be pretty nice. Okay, I was just checking to see how much room I had there. So, I will see you in the next video. Thanks for watching.